Dear students, after studying this module, you shall be able to know about the Sn2 reaction, that is bimolecular nucleophilic substitution reactions. You shall be able to learn the kinetics and the reaction mechanism of these Sn2 reactions, identify the stereochemistry of Sn2 reactions and evaluate the various factors which affect the Sn2 reaction. And you shall be able to understand some typical reactions such as Mitsunobu reaction and Williamson's ether synthesis. Let us begin with recalling the nucleophilic substitution reaction which occurs when the substrate is attacked by a nucleophile and the leaving group departs. The reaction takes place at a saturated carbon atom, that is, which is sp3 hybridized. Nucleophilic substitution reactions which follow the second order kinetics are known as Sn2 reactions. The rate of second order reaction depends upon the concentration of both, that is the substrate as well as the reagent. The term Sn2 stands for bimolecular nucleophilic substitution. These reactions are completed in a single step by the displacement of a leaving group by a nucleophile and no intermediate is formed, rather there is a formation of a transition state that we will see. Sn2 reactions always goes through a possible transition state, and at the transition state the time of bond formation between the carbon atom and nucleophile is almost same as that of the breaking of bond between the leaving group and the carbon atom, because at no time can the carbon have more than 8 electrons in its outer shell. Therefore, the nucleophile approaches from the back and the configuration at carbon is inverted. Other way round, we can say, if the nucleophile attacking the carbon atom is opposite to that of the leaving group, then inversion of configuration takes place. Now, you can see here in this mechanism as shown, the nucleophile attacks from the back side. And why the back side attack happens? Because there will be repulsion between this negatively charged nucleophile and also the X, which is also electron rich. So, rather it prefers to attack from the opposite side of that of X, and another thing is there is less steric hindrance on this side. So, this nucleophile attacks from the back side, and as a result we get this transition state. You can see that here the attacking nucleophile and the leaving group X are partially being formed and being broken, and eventually the leaving group goes out and you get the product where you can clearly see the inversion in configuration happening if we start from a chiral carbon. Let us now discuss this in more detail. Sn2 products are stereospecific because stereoisomeric reactant gives stereochemically different products. They are also stereoselective because they form exclusively or predominantly only one of a possible pair of enantiomers or one of the possible diastereoisomers. Now, let us take an example to understand this Sn2 mechanism in more detail. Let us consider the reaction between methyl bromide and the base OH minus, which is the ion generated from NaOH. The rate determining step involves both CH3Br and OH minus. The reaction between two reactants resulting in the direct displacement of Br minus and OH minus group occurs in such a way that a new COH bond is being formed while the old CBr bond starts breaking. Thus, the bond formation and bond breaking occur simultaneously, and hence the reaction is a one step reaction without any intermediate being formed. While the reaction is taking place, the energetic OH minus ion approaches the CH3Br molecule from the opposite side of the bromine to avoid the repulsion between the OH minus and Br minus ions. In the reaction medium, the OH minus ion approaches the electron deficient carbon atom, following which the CBr bond starts stretching, and at one stage both the Br and OH are partially bonded to the central carbon atom, which is represented by OH dash bond C, then again dash bond and Br. And this is known as the transition state. You can see here that in this transition state you have OH, C, Br linked with these dotted bonds, that is being formed and being broken, and further on the carbon is joined to the 3 substituents it was already joined to in the substrate. In the transition state, the partial negative charge of OH minus ion is transferred to Br through the central carbon atom. At last, the approaching OH minus ion results in the formation of the complete COH bond, and in this process Br minus ion departs. In the transition state, as you can see here, a total of 5 atoms or groups are attached in the central carbon atom. And as we move in the series from methyl bromide to tertiary butyl chloride, that is from primary to the tertiary halides, a decrease in the nucleophilic attack is found at the carbon bearing the bromine atom due to the steric hindrance of the attached group or atoms. In case of moving from primary to secondary to tertiary, the steric hindrance is increasing. Or we can also say that the nucleophile does not get any space to attack. The plus I effect along the series makes the carbon bearing the bromine progressively less positively polarized and consequently less readily attacked by the nucleophile. So, you can see here that the substrate CH3Br is being attacked by this nucleophile OH minus from the back side, leading to this particular transition state, and then eventually the Br minus, which is the leaving group, departs and you get the product which is methanol. And if we start with a chiral carbon, then it will lead to the inversion in the configuration. If we compare the rate of hydrolysis of alkyl halides, then what we find is it is in the order of methyl halide will be most reactive, followed by primary, followed by secondary, followed by tertiary. And we can say that the steric factor is more important than the electronic factor. The E activation, that is the activation energy required for the formation of transition state, will be highest for tertiary and least for the methyl halides. The reaction is thermodynamically favorable only when a stronger base replaces a weaker base. Hence, successful displacements are exothermic. Let us consider an example to understand the Sn2 mechanism. Now, in this example, you can see that we are starting with this methyl bromide, which is the primary halide, and this OH minus is attacking on this carbon, which is being made electron deficient because of the minus I effect of this bromine. So, notice that this OH minus is attacking from the back side, that is as compared to this Br, it is the back side of this molecule, and it results in this transition state. And you can notice that in this transition state, this CBr bond is in the process of breaking, and simultaneously the COH bond is in the process of making. Further, what happens is slowly and slowly the CBr bond breaks and you have the removal of Br minus, and this part will be giving you the product which is CH3OH. So, this is how the Sn2 mechanism is taking place. Let us consider another example, and where we have this carbon joined to, let us say, Br, and now let us take this as a chiral carbon, and in the what we take is, let us put a D here and we put a methyl here. So, again you can notice that because of the minus I effect of Br, there is delta minus on Br and there is the electron deficiency on carbon. And now as this molecule is attacked by OH minus, this OH minus will be attacking from back side and it will result into the transition state where these three substituents, that is H, CH3 and D, are in one plane and the CBr bond is partially broken and the COH bond is partially formed. So this is what is the transition state, and you can notice that here there will be delta minus on both of them, and further what happens is it will be undergoing the cleavage here. So this Br will take these electrons along and go out as Br minus, and what we get as the product will be is this inverted alcohol, and if we start from D we will be getting L, and if we start from L we will be getting D. So this is what is the inversion in configuration, which has been referred to as Walden inversion. So you can see here in this equation shown, that is the free energy delta G is given by delta H minus T delta S. You are already aware about this relationship, and here delta S, that is the entropy change, is equal to the entropy of the transition state minus the entropy of the starting substrate molecules. And shown here is the energy diagram for the Sn2 reaction, and you can notice that as we are starting from combination of a nucleophile with methyl halide, for example here OH minus with CH3Br, then this much is the activation energy which is required for these to reach to the formation of transition state. So this area is representing the transition state, and further on it will be giving rise to the products, that is if you start from Nu plus MEx, then you get MENU and X minus, and for example here starting from methyl bromide reacting with OH minus, you will get methanol with the removal of Br minus. So you can see here that the products and the starting molecules, the products are having lower energy, and that is what is again the driving force for this reaction. If we look at the kinetics of Sn2 reaction, in the Sn2 reactions both the substrate, that is we have considered the case of CH3Br, and the nucleophile, like we have considered the example of OH minus, they take part in the rate determining step, which is the only step, and the reaction should be first order in each component and hence second overall order, and they satisfy this particular rate expression as you can see here, that is the reaction follows second order kinetics, and the rate equation is given by rate is equal to K, which is constant, multiplied by the concentration of CH3Br, that is the substrate, and multiplied by the concentration of the nucleophile, which is OH minus here. This law was found to apply for many reactions in chemistry, but for reactions involving excess of nucleophile or solvent, even though the mechanism is bimolecular, experimentally determined rate will be first order, and this is because the rate is dependent on the concentration of the substrate molecule. The kinetics involved in this reaction is referred as pseudo first order, that is the rate is given by K times the concentration of methanol. The unfortunate part is that the reaction mechanism can't be operated for the substrate containing the leaving group at the bridgehead carbon atom of any polycyclic systems, and the reason is that the backside attack of this carbon can't be free to allow the nucleophile from that side during the formation of a transition state. Now let us apply the Sn2 on some bicyclo compounds, and for that let us consider this 2,2,2 bicyclo system as you can see here, where when it is reacted with ethoxide ion, there is no reaction happening. And why it is so? You can clearly see that the position of this Br in this bridgehead is at such a way that there is no backside attack possible, because this entire ring will be creating the steric hindrance and this ethoxide ion cannot do the backside attack for the Sn2 to happen. So, there is no reaction in this case. Similarly, when you look at this 3,3,1 bicyclocase, then what you find again here is that this Br is so positioned that when this molecule is reacted with sodium iodide and acetone, which provide the appropriate Sn2 condition, but still there is no reaction because the iodide ion cannot do the backside attack on this ring, which is acting as a steric hindrance for the backside attack. Another example, if we take case, is the isotopic labeling experiment, and this may provide evidence for the complete inversion of the absolute configuration by Sn2 reaction. The reaction between optically active 2-octyl iodide and the radioactive iodide ion results in a mixture. If the reaction started with a pure R isomer, initially S isomer of radioactive 2-iodooctane is formed due to the exchange of iodide ion by Sn2 mechanism. Once a significant quantity of S isomer is produced, the same kind of iodide exchange with the isomer yields the R isomer again. And due to the establishment of equilibrium in the later stages, the reaction mixture was obtained. And it is because the rate of inversion and the rate of exchange of ion is almost the same. And it has been found that the rates are identical within the experimental era. So, you can clearly see here that this 2-iodooctane, when it is reacted with I minus, you are getting this product where the normal iodine is getting replaced with the labeled iodine, but then eventually it will lead to the equilibrium and you get the mixture of 2-iodooctane, which is simple, that is without labeling, as well as 2-iodooctane where iodine is labeled. And here you can see the rate of inversion is 2.88, and you can see with these values of rate of inversion and rate of exchange that they are very close. Now, after this, let us move to the linearity of transition state. Sn2 and co-workers, they postulated transition state in Sn2 reaction should be linear. The base treatment of methyl alpha tosyl O-toluene sulfonate results in O1-tosyl ethyl benzene sulfonate, as you can see in this equation. And in this reaction, base is used to remove alpha proton, which results in the formation of an anion, and thus this reaction may undergo an internal nucleophilic substitution reaction. You can clearly see from this particular equation that as this methyl alpha tosyl O-toluene sulfonate reacts with OH minus, then the CH2 group joined to tosyl group generates the carbon ion, and then this carbon ion will be further attacking as a nucleophile and take the CH3 from the sulfonyl and take this methyl group and leaves the SO3 minus. So, what we get as a result is O1-tosyl ethyl benzene sulfonate. The carbon ion produced here was believed to act as an internal nucleophile and attacks the methyl carbon of sulfonate ester by intramolecular mechanism. If it is linear, the transition state cannot be achieved, but later the crossover experiments of this reaction have showed that the negatively charged carbon attacks the methyl group of another molecule rather than the nearby one in the same molecule. That is, this is an intermolecular reaction and not intramolecular reaction, which it seems to be, and this confirms the linear transition state. In intramolecular reactions, linearity of transition states can be very difficult, because they will be arranging in a cyclic way and that will be difficult to attain. Let us move to the stereochemical factors of Sn2 reaction. From the above discussion, it can be concluded that the molecule is turning inside out, or we can say direct displacement, and thus Walden inversion. This Walden inversion was named after the scientist Paul Walden and is expected to take place when you are having a Sn2 reaction. When a substitution takes place in a chiral carbon, inversion of configuration occurs, and this is known as Walden inversion, and it was observed long before the Sn2 mechanism also was formulated, and this mechanism of Sn2 was formulated by Hughes and Ingold. And in the Sn2 reaction, the alkyl halide gets converted into alcohol in the presence of strong base and results in this inversion. The change of configuration can be established by observing the directions of optical rotation. Examples of Walden inversion can be like chlorination of plus malic acid results in plus and minus chlorosuccinic acid, while similarly hydrolysis of plus chlorosuccinic acid results plus and minus malic acid. In these reactions, one must be an inversion while the other must be retention of configuration, but it is not possible to predict the exact point of inversion. So, you can see here that in these equations, starting from plus malic acid, when you do the reaction with SO2Cl, then plus is being retained into plus chlorosuccinic acid, but when this is reacted with PCl5, then we are getting the minus chlorosuccinic acid. Similarly, when we start from plus chlorosuccinic acid and do the reaction with KOH, we are getting minus malic acid. There is inversion happening, and when it is reacted with silver oxide in the presence of aqueous medium, then we are getting plus malic acid. Phillips and co-worker reported that the prediction of exact position of inversion. Let us now consider some examples, and first of all let us take the chlorination of plus malic acid. Now, as you are aware, the plus malic acid has this structure, and let me show this OH with a different color. And now what we notice is that when this plus malic acid is treated with SO2Cl2, this OH gets replaced with Cl, and it happens via the retention in configuration, that is from plus we will be getting plus. So notice that this OH has been replaced by Cl, and this has happened with the retention in configuration, that is we are getting the plus chlorosuccinic acid, which is this molecule. On the other hand, if this molecule is treated with PCl5, what happens is there will be now inversion happening, that is from plus we get minus and we get this molecule. So notice that in place of this OH, now this Cl has come, and this reaction takes place via the inversion in configuration. Another example let us take is the hydrolysis of plus chlorosuccinic acid. Now here notice that this chlorine, if we want to hydrolyze, that is we want to replace with OH, it can be done with either KOH. So when we take the KOH as reagent, then starting from this plus we are getting inversion, that is we are getting the minus malic acid, and the product will be this minus malic acid. And notice that Cl has gone into OH, and that has happened with the inversion. So from plus we are getting minus. On the other hand, we can carry out this reaction by retention in configuration, and that is done with the help of aqueous silver oxide or silver hydroxide alternatively. And what happens is we will be getting the malic acid, but this time there is a retention in the configuration, that is from plus we are getting plus only. So these are the malic acids, and this is just the reverse of the reaction what we have studied just now. And we can carry out the reaction, that is hydrolysis of chlorosuccinic acid, by replacing this chlorine with OH, either by the inversion as happening here with KOH, or with the retention in configuration as is happening with the aqueous silver oxide. Did fabulous work to establish the inversion of configuration in Sn2 reaction. For example, reaction of plus 2 iodooctane with the radioactive iodide of Ki. It results in minus iodooctane, and the rate of the reaction is as shown here. The rate is directly proportional to the 2 iodooctane concentration multiplied by the concentration of iodide ion, which is labeled. Thus, the exchange of actual iodide with the radioactive iodide results in the loss of optical activity, which indicates the formation of minus isomer from plus isomer. Thus, inversion of configuration indicates the Sn2 reaction. So, as you can see in this mechanism, that starting from the 2 iodooctane where iodine is not labeled, and when it is reacted with radioactive iodide as nucleophile, there will be formation of this transition state, and then from this transition state, as the unlabeled iodide goes out and the labeled iodide is attached from the other side, there is a formation of minus 2 iodooctane, that is inversion in the configuration. So, this was proved by Hughes and Ingold. Let us look at the factors influencing the Sn2 reaction. First of them is solvent. Nucleophiles are more stabilized than the transition state in polar protic solvents due to solvation, where ground state energy of nucleophile is reduced in comparison to the transition state's energy. And due to this, the reaction progress leads to a higher activation energy and thus to a lower reaction rate. The nucleophiles are less solvated in polar aprotic solvents like DMSO, DMF, HMPT, etc., which results in the less stabilized ground state when compared to the polar protic solvent. Thus, the nucleophile is more reactive, which leads to the lowering of activation energy and a higher rate of the reaction. Thus, for Sn2 mechanism, we can say increasing the solvent polarity usually decreases the rate of reaction. So, we should prefer the non-polar solvents, that is polar aprotic solvent should be avoided. The next factor is the nucleophile, and in Sn2 reaction the nucleophile is involved in the rate determining step. So, the nature and concentration of the nucleophile will affect the rate of the Sn2 reaction. The stronger the nucleophile, the faster is the Sn2 reaction. In Sn2 reaction, the high energy transition is required. Therefore, a high concentration of strong nucleophile is required for Sn2 reaction. Good nucleophiles having higher energy in the ground state are less stable than the poor nucleophiles. Thus, the activation energy in Sn2 reaction is lower and the reaction rate is consequently higher than in Sn1 reaction with a comparatively stable nucleophile. The reactivity of small nucleophiles is rapid than the sterically demanding nucleophiles. Basic and negatively charged nucleophiles are more reactive as compared to uncharged nucleophiles. Coming to the next factor is the substrate itself. Activation energy of the transition state in Sn2 reaction increases as the steric hindrance in the substrate increases, while at the same time reaction rate is decreased. The reaction rate of Sn2 reactions will be in the order, that is primary is most reactive, followed by secondary, followed by tertiary alkyl halide. and in the case of secondary and tertiary alkyl compounds, the Sn2 reaction is largely superseded by an Sn1 reaction or elimination. Rates of Sn2 reactions for allylic and benzylic systems are also increased because of resonance in the transition state. Coming to the last factor is the leaving group. A leaving group which becomes a more stable species after it departs is a better leaving group. The best leaving groups are the weakest bases. Stable anions are good leaving groups which result in the lowering of activation energy while reaction rate is higher. For example, iodide anions are better leaving groups than chloride anions. Hydroxide anions, alkoxide ions, fluoride anions, amide anions on the other hand are poor leaving groups, and thus Sn2 reactions with fluoroalkanes, alcohols, ethers or amines virtually never occur. And if you recall, if you have to do it with alcohols, you have to first protonate and make it as a good leaving group as water, and then only the nucleophilic substitution can occur. However, acid catalyzed Sn2 reactions with alcohols or amines can take place, as the leaving group here does not consist of the hydroxide ion, rather they will be as water and ammonia. Thus, the leaving groups can be arranged in the order as shown here, that is MsO minus and TsO minus are very good leaving groups, followed by I minus, Br minus, then Cl minus, F minus, and then followed by OH minus or NH2 minus. Actually these two are very weak leaving groups, and as such they will not undergo the Sn2 mechanism. Only in the acidic medium they will give rise to reactions. So, MsO minus and TsO minus are extremely good leaving groups, and that is due to the resonance stabilization. So, more is the stabilization of the anion, better leaving group it will be. So, thus the nature of leaving group not only affect the rate of reaction, but also may change the reaction mechanism. Now, look at some of the examples of Sn2 reaction mechanism where it is happening. As you can see in this equation, when phenol is reacted with NaOH, you get this phenoxide ion, and when this phenoxide ion is further reacted with this molecule, you can see it will be attacking on the CH3, which is being made electron deficient by this OSO3 CH3 group, and you get this corresponding ether, and this tosylate group is a good leaving group. Another example that you are already aware is Williamson's ether synthesis, but here we will see that how the Williamson's ether synthesis, ROH is reacted with sodium hydride to generate the RO minus Na plus, that is the sodium alkoxide, and when this sodium alkoxide is reacted with any alkyl halide, preferentially the primary halides, which will undergo Sn2 mechanism and give you the corresponding ether. Like here we are reacting with CH3I, and the RO minus will do the backside attack, I minus goes out, and we get the ROCH3 as the product. Another example you can see here as shown, the ammonia attacks from backside. So, here it is the C joined with CH3 H and H Br, and as ammonia attacks Br minus goes, you get NH3 plus, from which one of the proton will be removed, and eventually you get NH2 as the group which has attached in place of Br, or NH2 which has substituted the Br via the Sn2 mechanism. Another example you can consider as shown here is that this vinyl chloride is one, and there is another chloro which is at allylic position. So, you can clearly see that out of this vinylic chlorine and allylic chlorine, when we are doing the reaction with sodium carbonate in aqueous medium, then the water will be attacking as a nucleophile and replacing this allylic carbon without affecting the vinyl chloride, and that is how there is a Sn2 reaction happening at this allylic chloride. Another example, if we consider, let us take this CH3 CH2I, and when this is reacted with this particular reagent, where S is bearing the minus charge as the nucleophile, then this attacks and there is a removal of I, and in place of I you get S joined to CSOET, and here also you can see this is going via the Sn2 mechanism. Similarly, you can see another case here, that starting with plus S2 butanol, when it is reacted with tosyl chloride in the presence of pyridine, then OH gets replaced with OTS, and notice that there is retention in the stereochemistry as the CO bond is not being broken here. But further on, when this S2 butyl tosylate is reacted with tetrabutyl ammonium acetate in the presence of DMF, then this OTS is getting replaced with OAC. So, this OAC minus will attack as a nucleophile from backside, and in this stage the Sn2 mechanism is happening, and you can notice from S you are getting R2 butyl acetate, and further on this OAC can be hydrolyzed by tosyl chloride and pyridine, you will get OH in its place. So, this step again there is no change in stereochemistry happening because the CO bond is not being broken, and what you get is overall, if you now compare the starting molecule from plus S2 butanol, we have been able to convert it into its enantiomer, that is minus R2 butanol, by adopting these intermediate reactions, where one is undergoing without change in stereochemistry and one is undergoing change in stereochemistry, and overall there is a inversion which is happening in this reaction. Another example, if we see, Sn2 reactions are possible at elements other than carbon also, namely silicon, phosphorus, sulfur and the halogens. And as an example you can see this case here, where triphenylphosphine attacks on CCl4 and one of the Cl is taken by phosphorus, and you get this triphenylphosphonium chloride, and left is CCl3 minus. So, you can see it is the Cl plus taken and CCl3 minus is left. Furthermore, this CCl3 minus will be attacking at this electron deficient phosphorus and gives rise to this molecule by the removal of Cl minus. So, you can see this step is the Sn2 mechanism happening, where the CCl3 minus is attacking as a nucleophile from backside and Cl minus departs via the Sn2 mechanism. Another example, if we see, the alcohol here is attacking on silicon in place of carbon, and as it acts as the nucleophile from backside, then Cl minus goes out and we get this protonated ROH attached, from which the proton will be removed by the Cl minus acting as the base or another base in the medium, and that is how you get this Sn2 product, where in silicon in place of Cl now you have OR, but with the inverted configuration substituted. Another example you can see here is this phenyl ring joined to COCH2Br, and as this is reacted with this molecule, then this nitrogen through the lone pair attacks as a nucleophile, and it will attack on this CH2 and make the substitution in place of Br. So, this also goes via the Sn2 mechanism. Let us consider one named reaction, which is Mitsunobu reaction. Here the reaction between primary alcohol and nucleophile in presence of triphenylphosphine and diethyl azo dicarboxylate, which is abbreviated as DEAD, leads to the selective and inverted Sn2 product. And the example of Mitsunobu reaction you can see as being shown here in a general way, where ROH reacts with NUH, NUH is the nucleophile, and in the presence of triphenylphosphine and this DEAD, we get the substituted product, which is RCH2NU, and there will be inversion here. So, let us see the mechanism here, and as you can see that triphenylphosphine will attack on this nitrogen, and as a result the double bond pi electrons get shifted to other nitrogen and we get this particular nitrogen anion. This nitrogen anion, that is nitrogen with minus charge, will be acting and attacking as base and take out this hydrogen from the alcohol which is there in the medium. And that is how from this alcohol there will be generation of this O minus, that is the alkoxide ion as a nucleophile. And this particular species you can see is also resonance stabilized via the electron withdrawing COOET group, that is from N minus the O minus can be formed via this conjugation. Moving further, this RCH2O minus will be attacking on the positive part of phosphorus, and as it attacks then these electrons further move toward the nitrogen and the PPH3 gets cleaved from this species, and what you get is RCH2O PPH3 with a plus charge. Furthermore, this N minus which is formed in this earlier step will be taking out the proton from the nucleophile that we are adding and generate the Nu minus, and this further Nu minus will be attacking on the CH2 further joined to OPH3 plus, and as the Nu minus attacks on this CH2 via the backside Sn2 mechanism, then this PH3PO will go out as a leaving group, and that is how you get the substituted molecule which is RCH2Nu starting from RCH2OH. So, that is how we have been able to replace the OH with the nucleophile, and this is what is the Mitsunobu reaction. Another example you can see is where this alcohol, where O has been differentiated and labeled as B, is being reacted with this carboxylic acid, and this particular oxygen is A, and when this is reacted with the triphenyl phosphine, then what you get is there will be combination of these two and you get this ester, and in this ester notice that this oxygen is coming from carboxylic acid, not from the alcohol, and this is also going via the Sn2 mechanism. So, dear students, let us summarize what we have learnt in this module. You have learnt that primary and secondary alkyl halides reacting with nucleophiles, they follow Sn2 mechanism, and we have revisited how the Sn2 mechanism takes place. The reaction rate depends on both the substrates as well as the nucleophiles concentration, and it is a second order reaction. These reactions occur always with the backside attack, and in the backside attack the nucleophile attacks the substrate from opposite side of that of the leaving group, which results in a stereo inversion and is referred to as Walden inversion. In the reaction centers, number of substituents groups are higher, the rate of reaction of Sn2 will be lower, and thus Sn2 reaction is then superseded by Sn1 reaction or even elimination. Order of Sn2 reaction we have seen for alkyl halides is the methyl halides will be most reactive, followed by primary, followed by secondary, and followed by tertiary, where the tertiary are the least reactive towards Sn2 reaction. Substituents in the position adjacent to the reaction center reduces the reaction rate. More effective the nucleophile, higher will be the rate of reaction. Soft bases do not contain bulky substituents are usually good nucleophiles. And we have also seen that weak bases are often good leaving groups, which will help the Sn2 reaction. And polar aprotic solvents do not reduce the reaction rate, and it is how non-polar solvents will be helping the Sn2 mechanism.